Hi everyone, welcome to another episode of the Data Science Decoded podcast. As far as I can count, this is episode number 7. So we're getting quite far and good that we're consistent, almost like an estimator. Okay, I'll stop with the jokes. Mike, how are you today?
I'm okay. I have a great background. I'm in my apartment, but my background makes me feel that I'm in a different place. I plan to go on vacation in a bit less than 2 weeks, so I hope my flight won't be cancelled. It's common situation, and nice to see you again. And let's talk math.
How was give a few sentences about the paper?
Yes. You want me to give a couple of sentences about the paper?
Yeah. Before we move to Nir.
Okay. This paper is of Fisher. I think in our first episode we discussed another seminal paper by Ronald Fisher, by Sir Ronald Fisher, I guess. And this paper actually introduces something that we know as linear discriminant analysis. And we're going to discuss this very important notion, very important also in math and also in the machine learning. It is widely used, almost widely as a linear regression. And this paper is short, so our episode not going to be very long. You're not going to suffer for a very long time. So now
God's
it's
willing,
Nir's turn to talk.
Hi Nir, how are you?
Good. I'm doing good. Yeah, it's still the weekend here. It's Sunday. It's sunny outside. So I'm going after this recording. I'm going to go out a little bit, soak a little bit of sun. But until then, yeah, we have some ground to cover here with linear discriminant, and I would also add an example of ANOVA, right?
Oh, yeah, analysis of variance, right?
Variance, yes.
Because
yes.
the ANOVA is the algorithm ANOVA as we know it today, excluding the F test and the p-value, was suggested by Fisher, I think, in a previous paper, and here he gives an example.
Yeah.
Okay.
We'll get to that. That's true. I also saw something that is relevant. Cool.
We started the word variance, so which appears in the ANOVA abbreviation. So maybe it is here in this paper.
Yeah, and what I wanted to say. So, to me, it was a shorter paper than previous ones, but still I had some few questions, so we'll get to them. Hope you have some answers. And this paper is from 1936. Then it's called The Use of Multiple Measurements in Taxonomic Problems.
Taxonomic, yeah.
Taxonomic. Thank you, Nir. And what first popped out to my eyes, it's that the journal is Annals of Eugenics. Okay, so yeah, today this is quite a forbidden topic, but back then, I don't know if genetics was already popularized as a topic, but eugenics for sure started in the end of the 19th century. And there was, of course, a lot of overlap because they studied various species, including humans. So that's why that's the name of the journal. And I read, and they changed it in 1950 something. The Annals of Eugenics was changed to I think something of genetics. Journal of Genetics or something like that. So that was interesting history.
Okay. Daniel, by the way, do you know that the genetics was forbidden in USSR in 30s and maybe 40s, and
No, I didn't know that.
yeah, and very famous, how do we call it, genetician, very famous professor of genetics. Vavilov was put in prison. I don't remember if it was in the end of 30s or maybe 40s or 40s, but there are like saying that genetics is a pseudoscience. Russian. So I just translated from Russian. The genetics of pseudoscience, it doesn't exist. I don't remember what is not pseudoscience instead of genetics, but genetics was claimed to be a pseudoscience, not real science. Yes.
Interesting. Okay, thank you for that piece of history. I have some few things to say, but we won't digress. Let's jump to the paper. Yeah. Maybe for future discussions. So the first chapter, which is short, is termed discriminant functions. And Fisher says when two or more populations have been measured in several characters from x1 to, here it's x8, but let's generalize to xn, a special interest attaches to certain linear functions of the measurements by which the populations are best discriminated. So how can we distinguish between the populations? The other suggestion use has already been made of this fact in crinometry. So I read it something relates to the skull, I think. So they measured sizes of skulls or something like that, by Martin, who has applied the principle to the sex differences in measurements of the mandible, which is the jaw. As I also checked that.
Okay.
So they like measuring stuff. And also by Miss Mildred Bernard, who showed how to obtain from a series of dated series the particular compound of carnial measurements showing most distinctly a progressive or secular trend. So carnial is also something in the brain. So again, Journal of Eugenics. In the present paper, the application of the same principle will be illustrated on a taxonomic problem. Some questions connected with the precision of the process employed will also be discussed. Perfect. So taxonomy is the study of different groups or something like that. What's the exact definition?
Yeah, I think it's the study of these different classes.
Classes.
In this, I mean, for us, it's classification mathematically, but
Yeah.
more biologically, it's do these groups of biology existence share the same DNA? This kind of question.
Same genetics. DNA was found in
Yeah,
54.
genetics.
Yeah,
yes,
yeah.
yes.
They didn't know about it yet.
Yes.
Okay, so
By the way, very, really very small remark. Here we're talking about some linear transformation, which purpose is to separate examples of different classes at a maximal extent. And when we are talking about non-linear transformations, we have our deep neural nets. Okay, we have images of different classes, say rabbits, elephants, and we want to find some non-linear transformation as a deep neural network, which separates these classes at the maximal extent, maximally. So here it is linear, and when we come closer to our period, we will discuss in the same, not in a similar way. We will discuss neural nets.
Yeah, great point, and he gets to that. He's gonna do regression at some point later.
Yeah.
Okay, so second chapter called arithmetical procedure. So it says that table 1 shows measurements of the flowers of 50 plants of 2 species. So each species has 50 plants measured. The species are Iris setosa and Iris versicolor. And they found grown together and measured by Anderson. And he says thank you to him. And then he says 4 flower measurements are given. We shall first consider the equation the question, sorry, what linear function of the four measurements x, capital X, equals all the x1 to x4 features times lambda 1 to lambda 4. So we have like a linear combination. And he says which function will maximize the ratio of the difference between the specific means to the standard deviations within species. Okay, so he's trying to take the features and do some kind of optimization to find those lambdas. Am I correct?
Mm-hmm.
Yes.
Cool.
By the way, it is interesting why he's talking about the ratio of mean and the variance, because this ratio somehow describes the how each species is distributed, how wide is distributed. If the variance is very small, so it is condensed in a very small region, and then the difference between variances are very big. So you have two clusters, very dense and small clusters, which are located very far one from another. And if the variance is big, we may have the two clusters, which means are quite far one from another, but these clusters are very dispersed, so you can hardly separate between species of different classes, and this is the reason why he's talking about mean to variance ratio.
Yes, I think there is also another reason here, that if we think about it statistically, the statistic that is the mean difference divided by the standard deviation or variance is the T statistic, right? The student T statistic. And there were tables for that statistic.
I see.
So they can do some. Later on, he's actually in the paper. He's actually assuming that it's Gaussian, but doesn't matter. It's still this is a tool that they were employing back then, which is a lot of I think chi squared, T student, and Gaussian and normal. So that's another. I think they were just very much accustomed to think like that in terms of statistics. So he's trying to minimize the statistic, which is exactly what you said, Mike.
Yeah. By the way, as far as I remember, there is a name to this ratio of mean and the variance. Maybe it is a ratio between mean and standard deviation. It is called volatility in economy, right?
I actually thought I have a nice thought about it, but I'll save it when we get there. I just want to add something to the listeners, that the features x1 to x4, it means that every flower, so there's two species, 50 flowers per species, so on each flower they measured like 4 features, and they'll talk about like the petal and something else. Is the famous iris data set that everyone uses in Python and like sklearn to do basic toy problems, right? So that's the motivation behind this paper, Nir.
Yeah.
Just a small reminder. So I'll continue. He says, since 50 plants of each species were used, these sums contain 98 degrees of freedom. We may represent these sums of squares or products by capital S of PQ, where P and Q take independently the values between 1 and 4. So this is the features. So it's like a covariance matrix or something like that.
Is it covariance, Nir? I think you gave another name.
No.
I think it's a cross correlation, autocorrelation matrix. Yeah.
Yeah, cross correlation. Yeah.
Because to get the correlation, you need to subtract the means multiplied one by another. Yeah. From this auto, what is the name?
Cross correlation.
Cross correlation. Yeah.
Cross correlation matrix. Yeah.
Then he says, then for any linear function x, that's the function we're trying to find of the measurements, as defined above, the difference between the means of x in the two species is capital D, lambda 1 times d1 plus lambda 2 times d2 up to lambda 4 times d4. So now instead of multiplying the lambdas by the features x, we multiply them by the distance.
He's actually, if you scroll up a bit, he's actually taking the mean of the first equations there. So he's just taking the means of different equations and subtracting them. Calling it subtraction D. Yeah.
Cool.
Yes.
And then he says why the variance of x within species is proportional to, and then there's capital S, there's two sums from P from 1 to 4 and Q to 1 to 4 because there's 4 features, lambda P times lambda Q times SPQ that we defined as the cross correlation. He says the particular linear function which best discriminates the two species will be one for which the ratio is d squared divided by s, and which is greatest. And that's what I wanted to say. When I saw that, I thought about near, and I thought about signal to noise ratio.
Yeah.
Because it says d is the distance between the two species. So I want to maximize it because I want to separate them. So this is the signal. And denominator is s, which is the variance, and or this cross correlation. So how noisy is the measurements inside each class? So I thought about, he's trying to maximize the SNR. What do you think about that, Nir?
Yeah, I didn't think about it, to be honest, but in this way, but it makes perfect sense. Yeah, the signal is what moving away the hypothesis, right, from the noise. It's like if the noise is Gaussian and you have a constant signal, you will just shift it by mean, right? It's the same. So yeah, exactly what you said, Daniel.
Yeah, so that's what I thought.
Nice observation. Yeah.
By the way, in the beginning of the paper, he's talking about the ratio between the average, between the mean and variance. And here he's talking about the ratio between the squared mean and variance. And it is interesting. Maybe it is just a mistake in the beginning.
Yeah.
Because why are we using here the squared mean divided by the variance? Because we need them in the same scale.
Yeah.
Because because variance is a quadratic characteristics and the mean is a linear characteristic.
Yeah. So he wants to preserve units, the same units.
Yes, the same units. Correct, the same units.
Yeah.
Okay, so then he says if we want to maximize it, we need to do derivative or the partial derivative of this function by lambda, and the derivative should be equal to 0. So he does the math, and it can be shown, I guess, that it's equal to four linear equations.
Mm-hmm.
And he says the coefficients required, meaning the lambda 1, lambda 2, etc., are proportional to the solutions of the equations. There are 4 equations. And he says if in turn unity is substituted for each of the differences and 0 for the others, the solutions obtained constitute the matrix of multipliers reciprocal to the matrix of S. Reciprocal, I'm not sure what he means here, unity is maybe he decides that one of them will be 1.
Yeah.
Right?
Yeah. Because if you think about it, that's how we do linear discriminant analysis, right? We say the vector of output is 1 and 0, and then 0, 1, 1 and 0s, and then all each class have a 1, just one single one hat, so to speak, in each place. So he's saying if we instead of D1 to D4 we say 1, 0, 0, 0, we'll get the same matrix but proportional. That's what he's saying, and he's basically saying that this is a linear regression problem. At the end of the day, in this case, it's actually an inversion of a matrix, but in the general case, it's linear regression.
Yeah, so because it's linear, I think you can solve it like analytically by
Yeah.
So I just wanted to add here, we see in table 4, we can see the 4 features. It's the sepal length, sepal width, petal length, and petal width per flower. They measure that, and then they show the sums that they got for each one. So this is like the autocorrelation. Sorry,
Yeah.
cross correlation.
Yeah. The interesting thing, I think, they didn't call it features back then, right?
That's right.
Yeah, they call it
I say
measurement.
features.
Yeah. No, it's good. It's good that you say features. I'm just when I was reading this paper, I had in the beginning at least some learning curve to say, well, what does it mean by measurement? That it means the features? Yes, it means the features.
Yes.
Yeah. So we move to, I don't know if it's another, no, it's a continuation of the previous chapter. So he says that he solves the equations. So there's 4 linear equations, and he gets lambda from 1, lambda 2, lambda 3, and lambda 4. So again, it's like he solved the like a linear optimization problem, and which could, again, it was solved analytically because you can do the inverse of this S matrix of the cross correlation. You do the inverse, and then you can actually isolate lambda. So it's not even I wouldn't say it's an optimization problem. You can solve it analytically. Then he actually says, if we choose to take the coefficient of the sepal length to be unity, so here it says 1, the compound measurement required is, so now we have x, right? So once we have the lambdas, we can put them in and multiply each feature by the lambda, and it just normalizes. And so lambda 1 would be 1, and he gets this x transformation, again, linear transformation of the features. So now per flower, we can go measure his features, then apply this transformation and get this x per flower. And then he says, if in this expression we substitute the values observed in Setosa plants, so now we're looking on one species, the Setosa, the mean as found from the values is 12.33 centimeters. Okay, so after transformation, this mean, that's for the Setosa, and for versicolor, versicolor, that's probably the name. On the contrary, we have minus 21.42 centimeters. So we have like a difference of 33.8 centimeters between the two species.
Yeah.
Then he says.
So by the way, what he did here in the paper is called dimensionality reduction. We had 4 features, and we applied some transformation. In this case, it is linear transformation, and instead of that, we get 1 feature. We wanted to do. Yeah, we wanted to separate the species of these classes in a maximal way, but in the modern jargon of the machine learning, it is called dimensionality reduction. Maybe linear dimensionality reduction.
Yep. Yeah, 100%. We know that the linear discriminant analysis is a method for dimensionality reduction, right?
Yeah.
Also, the interesting thing about his paper is it doesn't deal with. He doesn't even bother to classify it. It's not classifying here. It's just an analysis, sort of an analysis of how good is this statistic, is this linear discriminant function.
It's like unsupervised in a sense. There's no trained test. You just try to use this.
It's supervised in the sense that he knows that this is versicolor and this is Setosa, right? He knows it. It doesn't want to discriminate. Yeah, but there is no. Is not trying to see how good is does this method work on a test set that we haven't seen before, so to speak.
It will happen in the last chapter.
He's just analyzing it. Yeah, last chapter, right?
Last chapter, he will add another species, and then he'll check what's happening.
Yeah, because if you If you go upper to the table in the previous page, you will see that there are 3 columns in this table and not 2. We have actually 3 species and not 2. I'm using here 2 as a train set and then 1 more as a test set.
Yes.
In the last chapter of this paper, right?
So I'll continue, and it says here, I won't go into the calculation. After we calculated the mean differences between the 2 species, he wants to calculate like the noise, the standard deviations. And he says here between a pair of plants of different species has a standard deviation of 4.7 centimeters. Okay, so just so we'll get this number. And now we continue to chapter number 3, interpretation. It says the ratio of the difference between the means of the chosen compound measurement to its standard error in individual plants is of interest also in relation to the probability of misclassification. Okay, so he says misclassification. So yeah, he wants to see how good we separate. What's the probability of us making a mistake, saying one species is the second, the other one, using our transformation that he calculated.
Yeah, in other words, how much these clusters of the species of the same of the same class are dense, and how far they are situated one from another.
Yeah.
In the other words, yeah.
He's saying here, supposing that a plant is misclassified if its deviation in the right direction exceeds half the difference of 33.8. So if you have the difference between 2 species, if you cross the middle, then you're misclassified. Okay, that's his definition. And here he uses again tables of statistics in order to calculate, because he knows the variance or the standard deviation in each species. That's like the noise. So he can calculate what's the probability of crossing the middle. And he says, I won't go into the calculation. I just want to see the result.
This is the Gaussian normal distribution table.
Here it says, we may therefore at once conclude that if the measurements are nearly normally distributed, the probability of misclassification using the compound movement only, compound movement is our transformation, is less than 3 per million.
Yes. Which is quite impressive for just a linear transformation of our features.
Yep. But again, he's first of all, he's doing it on a training set.
Yeah.
And second,
that's true.
And second, that's why I call it analysis and less classification. And then second, he's assuming that everything is Gaussian and they have the same standard deviations, so you can cut it in the middle exactly, and so on. Yeah.
By the way, there is some generalization of this linear discriminant analysis, which is called the quadratic discriminant analysis, I guess, which tackles the case when the variance of each species is different. Each class is different. Yes.
Okay.
But it is a bit more complicated from the mathematical point of view. More computations and more integrals.
Yeah, makes sense. So we move to chapter 4, the analogy of partial regression. So here now he's gonna compare it to a regression problem. He says if to each plant were assigned a value of a variate y, so it's like the label, the same for all members of each species, right? So each species of the flowers gets the same value y. The analysis of the variance of y between the portions accountable by linear regression on the measurements x1 to x4, the features, and the residual variation after fitting such a regression would be identical with table 6 if y were given appropriate equal and opposite values for the 2 species. So again, it's just saying here all species of one flower will get minus some number that he calculates here. The other species will get plus this number, and the difference between them is 1. So it's not just like we today say this is class 1, this is class minus 1. He calculates something else, but if we subtract them, it should be 1, the
Yeah,
difference.
like 0 and 1, I guess.
Yeah.
Yeah.
So he does here a regression problem.
Mm-hmm.
Again, you need to do the derivatives. I won't go into the math. Just let's go to the important points he say.
By the way, I think that this is, at least the way
How do you think about it? That's what you mean?
understood it. No, the way I understood it is that he's trying to say, I think it's something like what we call today leave one out. He's doing an analysis of a variance here and ANOVA, okay, and he's saying, okay, what is the contribution to the residual of this feature? Okay, so in terms of how do we do that, we basically regress on all other features and see what's the difference, right? That's one way to do that. And so he's trying to do something of this sort, I think.
Interesting. Here. I didn't think about it like that. I just thought the residual is just the error, so he can fit, and he knows the true measurements, so he just calculates the error, and that's what he called the residual. So I'm not sure.
I'm not sure either. Okay.
But he says test of significance. So he wants to show that if this fit is statistically significant, so it is now clear in what manner the specific difference may be tested for significance. So as to allow for the fact that a variate has been chosen so as to maximize the distinctness of the species. The regression of y on the 4 measurements is given 4 degrees of freedom, and the residual variation 95. The value of z calculated from the sums of squares in any one of the tables, or he said you can calculate it, and says a very significant value for the number of degrees of freedom used. So he says that it's statistically significant if you look at the value of z score is 3.21, which apparently it's a really high z score. So again, that's why he said here the residual has 95 degrees of freedom, because that's what I thought. He uses the actual measurements to calculate this residual as the error.
Yeah.
Okay, next chapter. Let's move in. Move to the next one. It's number 6, applications to the theory of polyploidy. Something like that.
This is a very tough word.
Yeah, I don't know if this field exists anymore, but as I tried to Google it and I forgot what it means. But I think it's all again related to some study of species, maybe in plants, because like pollen or something like that reminds me, right?
This is I think he's trying to answer the question if a class of flowers, I think it's Virginica, is a hybrid between the Setosa and the versicolor, like a genetic hybrid, like it contains both chromosomes of both species.
Okay, it is interesting.
Yeah, he writes here about chromosomes, about someone named Rodolphe. 2 years later, suggested the interesting possibility that iris versicolor is a polyploid hybrid of the 2 other species.
Yes.
So that's what you meant, Neil. So it's like a versicolor should be in the middle.
Yes. Yes. I mean, that's how he looks at it statistically when he calculates these linear discriminant values. He wants it to be in the middle, yeah.
Yeah, so now we're doing like we have a test set. So we build this transformation on 2 species. Now we get a 3rd species, and according to the to him or to somebody else 2 years prior, the third species should be actually to the farther away, so it's not in between.
Oh, I think it should actually be between, yes.
No, it should be between,
That's how
because
I
we
understand it.
trained, like we did the analysis on versicolor and setosa.
Yes. But if the Virginica is a hybrid of both, if you measure the distances,
No, but
like
it
the
says
distances of
versicolor is a hybrid of the two other.
versicolor, yeah.
And we
yeah.
trained on it, in a sense. We used it.
Yes, we did. We did.
I think they learned the linear transformation, and then they employed this linear transformation on the measurements of these three species.
Yeah, that's true.
And the result, he just got three different clusters, and these clusters maybe geometrically are situated in a way that one of the clusters is between because you have one-dimensional clusters, and one of the clusters between the two other clusters, and maybe with some coefficients, for example, 0.7 from the one and 0.3 from the right,
Yeah, you're now showing the plot that he did by hand, the histogram. Yeah. So on the x-axis is this dimensionality reduction to one feature that we discussed, is the linear transformation, and the setosa is on the left with negative values. The versicolor, whatever it's called, the other class is around 20, the mean. That's the other class we used for training, let's say. And then a new class came, the Virginica, and it's to the right.
Mm-hmm.
So the hypothesis that the versicolor, whatever it's called, is like a hybrid makes sense.
Yeah, but by the way, Neil, I have a question to you. As an expert in all this linear discriminant analysis, I revealed the secret that Neil just suggested talking about this paper, so I'll address my question to him. So what happens with linear discriminant analysis if you have more than two groups? Is there some generalization of it?
Well, to be honest, I don't know. I never used it for more than two groups.
Okay.
I think about it like the likelihood ratio test. So you do all the groups, like 1 and 2, 1 and 3, 1 and 4, and then 2 and 3, 2 and 4, and so on.
No.
That's not the efficient way to do that, but that's I think that's all they had back then. So I don't know.
Yeah. Okay.
Again, notice that there is no. He doesn't actually find the thresholds to classify between these three. He's not classifying. He's analyzing, and he's saying, okay, because it's in the middle, maybe it's a hybrid.
Yeah.
Now, to what extent? I never used it.
But that was the hypothesis prior. So he said somebody else said that it might be a hybrid. Let's look at my transformation. Well, it is in the middle.
Yes.
To some degree.
Yes. Yes, but if the fact that it's in the middle is saying that it's a hybrid, I don't know.
Yeah, I don't know.
Biologically, I don't know.
Yeah.
I just don't know. But he's trying to conclude statistically if this hypothesis should be rejected or not, and I think he doesn't reject it. But it doesn't mean that it is hybrid, right?
Yeah.
The fact that the test doesn't reject it.
I don't know exactly biologically what it means. That's true also.
Yeah.
And I wanted to say that when reading it, I thought, I should do like a binary classification problem, right? But probably they didn't. I don't know when the first binary classifier came about, because in a sense you need more computation to solve, even if you go to.
Wait. What do you mean by binary? Because this is what he's doing in the beginning. He's doing a binary classification problem. Unless you define it.
I define it in a modern sense.
Yeah, just logistic regression. He's not doing logistic regression. He didn't call it logistic regression, but actually he's kind of doing it. But
I think it's actually He's kind of doing it in the. You're right, Mike.
By the way,
No, it's
then
doing
I
linear
would.
regression. Or am I missing something?
Oh, he's doing linear regression, but a second. Let me.
But why he decided to do linear regression and not classification? Because regression, you try to regress something.
Oh, no. He's doing classification. He's just finding the coefficients for the classifier with linear regression or linear discriminant in this case.
I think that there's kind of confusion here, because what is actually linear logistic regression? Logistic regression, we're kind of trying to find a line, a straight line, which is best separating these classes. So after we find this line, we can use some logistic function to compute the probability, kind of probability of any point to be belong to class 0 or class 1. So we are looking for some straight line. By the way, there is another method called SVM, which is doing the same thing but in a different fashion. Okay, but here we are looking for this line which is best separating species of the different classes. And actually, then I was reading this paper, I have been thinking about how this line, the best separating line, in some sense, maybe in the sense of SVM, maybe in another sense of some other distance, how this transformation is related to this best separating line between these features, between these unaltered features before the transformation. And actually, I don't have an answer to this question.
Yeah, I think that this in this case, this is 4-dimensional space, so it's a hyperplane.
No, but he did dimensionality reduction to one feature, so it said it's in the middle.
Yes. When you look at one feature, it's in the middle. You're right. But when you look at the 4 features that he derived it on, so it's an hyperplane of 4 dimensions.
Yes, exactly.
And this is, by the way, even in 3 dimension, we know that the equation for a plane in the 3-dimensional space is z equals like a number equals ax plus by plus cz, right?
Yeah.
And this is exactly this equation. Yeah.
It doesn't matter. It doesn't matter which dimension the space has, because it is always the inner product between the coordinates and some vector of coefficients plus some constant. And equals 0. It is hyperplane, or we can call it straight line. I don't know what is the better term, but still it is the same thing.
It's the same thing. Yeah. And I think that the plane that is best differentiating is given in the equation that he finds with lambdas. That's the plane. That's this line, so to speak.
I think we can address this question to our listeners. Please comment if you know how this hyperplane, how this transformation is related to the hyperplane, which is best separates species of the different classes, because we don't know. Maybe you know.
Cool, interesting. Yeah, I thought about it now also.
Daniel, can you scroll up to the equation when you found lambdas?
Yeah.
Cool.
Just a second.
Cool.
What's happening to my Opa.
Okay.
At the beginning of the paper, right?
Yeah, it's almost the beginning. Yeah. That's. Can you scroll down? Scroll down.
But here, there's the lambdas.
Yeah, I know. But there is numbers. He finds the numbers for lambdas.
Okay, yeah, here.
Yeah, that's it here. So x equals x1 plus 5.9 x2. This is the best separating plane. That's it. That's the gist of linear regression. Of linear discriminant.
Yeah. Thank you for that. Now I get it.
Yeah.
Do you think so? I'm not sure about that. If we are talking about best separating plane in some sense, we need to define this sense, because I don't. Is it in the sense of SVM, support vector machine, or in another sense?
It's in the sense of d squared over the means. That's how he defined it.
Okay.
So scroll up a bit.
Yeah,
He's
just a
defining the
second.
sense in page 4, I think. Go to page 4. That's it. He's defining the sense and he's solving it mathematically by equating the derivative to 0. And he gets this linear system of equations. And he solved it. So this is the Fisher sense, the d squared over s, which the ratio d squared over s is greatest. That's the sense. So the maximum separation, as he defines it, is where like you said, Mike, is where the standard deviation are very thin for each class, and the separation in the means is very large. That's the sense he defines, and that's the actual sense of linear discriminant analysis that Fisher invented. By the way, I wasn't taught that in courses, in graduate level courses. I was taught another method to calculate the linear discriminant, which is equivalent. He's talking about that here. That is, it's a linear regression problem. You can put in one hat vector and so on. That's how I was taught that. But this sense is making sense, so to speak.
Perfect. Thank you. That was a nice paper.
Yep.
We need to think about next week. I thought maybe to do Turing or something, but we'll see. Also, for those who are watching, feel free to comment and propose ideas for papers. And that's everything on my side. Anything else, guys, to conclude?
No, it is very interesting and very short paper, and I love to discuss it. I think although with this paper is quite short, I think we dived quite deep into some interesting mathematical stuff. So let's try to do Turing next time.
Let's do it.
Yeah, unless something else pops up, which is more intriguing to us. I think that's the plan.
Okay. All right.
And I'll be in a different country.
Yeah.
Good.
Okay,
Yeah.
thank you. Have a
Thank
great
you.
week.
Bye, guys.
Bye, guys. Bye.